So I'm going to show you a way to, or something called a phase diagram, and it'll help explain the relationship between pressure and temperature and the particular phase that substance happens to be in at any one of those sets of conditions. So I have the three phases here: solid, liquid, and vapor. Now, if I'm going to go from a solid to a vapor, that is called sublimation. And sometimes you'll see that like on the road going up to Mount Bachelor. In the morning there's ice on the road, in the afternoon there's dry pavement. Well, the ice just sublimated. It just turned directly from a solid to a vapor. And when I go from a solid to a liquid, you're probably pretty familiar with that. That is going to be melting. And sometimes it's called fusion. So and we'll use that probably in the next chapter. When I go from a liquid to vapor, that's boiling. It's also going to be referred to as vaporization. Okay? Now, if I reverse these processes, if I'm going the other way, so let's say I'm going from a liquid now to a solid, that's freezing. Sometimes called crystallization. If I'm going from vapor down to a liquid, that's condensation. If I can write it all. Alright, and the last one would be if I'm going from vapor back to solid, that's called deposition. These are all physical changes and, the different phases of matter. Now, here comes the phase diagram. They're all going to take the same basic shape. I'm going to draw two of them. I'm going to draw a phase diagram of water and another one of H2O. Or no, water is H2O. I mean CO2. Okay, so I'm going to have two phase diagrams. They all have pressure on the y-axis, temperature on the x. So temperature is down here. And they're really handy little things to try to remind you, explain, well, okay, what happens to the boiling point if I decrease the pressure? Well, it's all explained right here. So pressure is here. Going up like that. Now for water, it's going to take this shape. There's three regions. Something like this. Right here, this will be where you have a gas. Right here, you're going to have a liquid. Right here, you're going to have a solid. And what this explains is the places at which, depending on what the pressure is or depending on what the temperature is, whether it is in a gas, liquid, or solid. So for example, let's use green. Let's say I'm right here, okay, and that's 1 atmosphere, 1 ATM. I'm going to wish that I had drawn this a lot bigger. Anyway, let's see. Alright, new plan. I'm just going to use P for pressure, now that I did it. So anyway, this is 1 atmosphere. Okay. If I go across, that's 1 atmosphere, 760 millimeters mercury, blah 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 blah. If I go across, I'm going to hit right there, where it goes from a solid to a liquid, that is melting, and that's going to happen at 0 degrees Celsius. And if I keep following that line across, boom, right there, that's where a liquid goes to a gas. That's vaporization, or boiling. That's going to happen at 100 degrees Celsius. So I can see what's going on. Now, in the class a day or two ago, I was manipulating the boiling point of water by decreasing the pressure. I mean, you can really see how that happens. At 1 atmosphere, the boiling point is going to be 100 degrees. But if I start decreasing the pressure going down, well, that's going to decrease the boiling point. So things become pretty obvious on a phase diagram. There is one interesting little point, and that happens to be where all of the lines intersect. And that's called the triple point. And a triple point is where all three phases coexist in equilibrium at the same time. And it's really not as bizarre as you would think. You've seen two phases coexisting. Anytime you have boiling water, you have liquid and gas. Or a glass of ice water, you have ice and liquid water. Well, at the triple point, you would have solid, liquid, and gas all going on. So it looks sort of like a glass of ice water that was boiling. But at the same time the boiling was going on, there was also some deposition going on, gas going back to solid, there was some condensation going on, and it's just this big circle. Well, anyway, for water, the triple point happens to be at 0.006 atmospheres. Make sure I'm right on that. Yeah. Really low pressure, and 0.01 degrees Celsius. Pretty low temperature. Okay. Well, I got to move on and get this done. So anyway, here's the triple point of CO2. It's going to have the same basic shape. Little different things that we can probably talk about a little bit later. Here I have a gas. Here I have a liquid. Here I have a solid. Okay. Again, pressure is on the Y. Temperature is on the X. And it looks very similar, but what is different is the points at which the phase changes are going to take place. For example, if I'm talking 1 atmosphere, down here, 1 atm, CO2, when it heats up, is just going to go directly into the gas phase. It's going to sublimate. And that's what you see with dry ice. It just starts, disappearing. You don't ever see any liquid CO2, because to see liquid CO2 it has to be at extremely high pressure. The triple point of CO2 happens to be, this point right there, happens to be at 5.2 atmospheres, so basically 5 times standard atmospheric pressure, and negative 57 degrees Celsius, so pretty darn cold. Now what accounts for the difference in these triple points, or where the lines go, happens to do with the makeup of the molecule. Water is a polar molecule, big time polar. If a molecule is polar, it's going to have high attractive forces, and it's going to have a lot of stickability to each of them. One water molecule is going to be able to stick to another water molecule. I look at CO2, and CO2 is nonpolar. Well, nonpolar have low attractive forces. There's not a lot of force, not a lot of stickiness. So this has low. Well, the low attractive forces account for the fact that, yeah, it's pretty darn hard to get CO2 to stick together. So hence the triple point, or where liquids are going to be present, are at relatively high pressure, still at low temperature. So anyway, that's it.